thanks so much for coming out to the talk. I'm really happy to be here. Let's get into it. So some background. My name is Bill Demirkapi. I'm a security engineer for the Microsoft Security Response Center. I have a background in low-level OS internals as well as cloud security. I've been working with Secure Boot for a little over a year now. And a fun fact, I was actually born here in Berlin. I'm really excited to be back after a little over 22 years. Okay, some background. What is Secure Boot? So Secure Boot is a security feature designed to prevent malicious software from loading when your machine starts. The TLDR is, let's make sure that any code that's executed is trusted and signed. In this talk, we'll be talking about the driver execution environment up to transient system load. So that's everything after the firmware has initialized, but everything before the OS starts. So the UFI firmware exposes dozens of crucial API that is exposed in a universal and unified manner. For example, load image lets you load a driver. With Secure Boot on, images must have a valid signature, but how does the firmware know who to trust? So this is where the DB, aka allowed signatures database, and DBX, the denied signatures databases, are particularly relevant. So from a high level, these signature databases usually contain either hashes or they contain certificates. You can create updates to these DB and DBX variables to control what is allowed to load and also what you want to prevent from loading in the first place. The signature databases are stored as authenticated variables. Now, what's an authenticated variable? What it means is that they can be read, but you can only write to it if you have a valid signed update payload signed by either the KEK key exchange key or the platform key. It's stored in PK. Now, every signed update payload also needs to specify an operation, and one of the useful operations we have available to us is called an append write. So let's say something goes wrong. There's a vulnerability in a UFI image. Append write lets us create a DBX signed payload with every single revocation up to that point. When you apply it to your system, it won't create duplicate entries. It'll merge with what you already have. And this is what really allows us to patch against UFI security issues. You know, when there's a vulnerable image, we can prevent it from being loaded in the first place. Now, on machines that ship with Windows, there's two common DB entries. Number one is the Windows Production PCA. This is typically used to sign Microsoft first-party images. And the UFI is typically used to sign any third-party code, like the Linux Shim. The UFI is why Linux works out of the box, even with Secure Boot enabled. You can take a USB, you can plug it in, and if it has Linux on it, it's going to work. Because how Microsoft and Linux distributions work together to sign a Shim, and the Shim is what lets Linux load their own images. Moving on to the threat model. So when Secure Boot is on, it's designed to protect against unauthorized code in your boot environment. This is a really common mistake I see some researchers make. Whatever loads after boot, like when in kernel mode or user mode, Secure Boot's not doing much against that. And another important fact is that when Secure Boot is off, you can already get code execution by design. Your code doesn't need to have a valid signature. This is an important fact that goes into our decision, why does MSRC call these vulnerabilities security feature bypasses? Well, if there wasn't this security feature, there is no vulnerability. You can already do whatever by design. So there's already a really high bar for exploiting Secure Boot vulnerabilities. But Secure Boot is crucial for enabling a chain of trust. Let's go through some vectors. For example, a local attacker might have admin and they want to persist in boot to get around antivirus. A physical attacker wants to install a rootkit or steal encrypted data. Think of an evil maid attack. An adjacent attacker wants to gain code execution on machines that have HTTP or PXE boot configured. A remote man-in-the-middle wants to gain code execution on machines that use HTTP boot. So, control over signature databases is generally exposed into BIOS. If you go into your BIOS provided by your OEM, chances are you can configure a lot about secure boot, like what keys are trusted and what's forbidden. The key fact here is that it requires physical access. The OS can make updates to these variables, but it needs to be signed. Whereas you, the machine owner, can go ahead in your BIOS and update these variables because you have proven that you have physical presence with the machine. Let's get into some attack surfaces of secure boot. So we're going to be covering a few different attack surfaces. This includes OEM firmware, custom OEM certificates, third-party images, the Linux Shim, and also briefly Microsoft images. Our focus is going to reside with the bolded attack surfaces. So one quick junction I want to take is with OEM firmware. So the embedded development kit is an open source and cross-platform firmware development environment. Many OEMs use a forked version of EDK2 in their code. Think of it as the golden standard. Now, there's a really big problem that other researchers have found with OEM firmware. What you can do as an attacker is that you can take your firmware, you can dump it, and identify, is this based on a shared code base? What version is it running? And once you find a repository, you can enumerate known bugs and abuse already patched issues simply because your vendor, your OEM vendor, has not got through with it. If you want to learn more about this vector, even though it's not the focus of this talk, I'd highly encourage you read The Firmware Supply Chain Security is Broken, Can We Fix It? By Binarly. Moving on to custom certificates. So OEMs will often ship custom certificates in DB besides what's already included by default, like the UFI CA and Windows CA. But unfortunately, these certificates have been found to sign dozens of vulnerable images. So let's go through a quick case study. In October, I built a PC with an Asus Tech motherboard. What attack surface did my OEM introduce? So what you want to do when you're starting out with analyzing your OEM's attack surface is dump the DB, the signatures, the allowed signatures database, and focus on the outliers. What is included on my machine that isn't included on other machines? So in this case, it includes the two Asus Tech motherboard and notebook certificates. It includes the canonical certificate. And it, in this case, also included 4 hard-coded SHA-256 hashes. Now, an interesting challenge with these outliers is that how do we find images that are signed by these entries? So Microsoft obviously has logs for stuff signed through to UFI or Windows CA. But what your OEM signs, we don't have any direct visibility into. Well, I want to introduce you to VirusTotal, which is a malware scanning platform that allows you to search for submissions using filters. So what I found was I can take, for example, the canonical certificate, take its thumbprint, and then do a signature search based on that thumbprint. This is a way we can get visibility into images, even if it's not a CA that we own, by using platforms like VirusTotal. Unfortunately, canonical certificate was used to sign several vulnerable Shim bootloaders. You can see that the first seen date is all the way back in 2013. There are a lot of vulnerabilities in this code that an attacker can abuse on Asus machines, simply because they include this certificate. And here's a fun fact. I actually asked the Linux community, particularly Canonical, did you have some agreement for including this certificate, which would make sense? What they told me was that Asus is actually shipping a really old version of their certificate, and no one has managed to make them stop. What about the 4 unknown SHA-256 hashes? Well, it turns out that they're actually hard-coded the SHA-256 hashes of old Windows boot managers, all the way from a decade ago, with known vulnerabilities. Now, this is not just an Asus Tech problem. In fact, most OEMs ship custom certificates. Firmware has the same problem. There's a lack of oversight from OEMs. With custom DB entries, it's really up to your OEM to keep you secure, because they get to decide what they want to include and what to revoke. There's only so much a company like Microsoft can do as a third party. All right, moving on to third-party UEFI images. So third-party UEFI images are where most of the security vulnerabilities in UEFI drivers have been discovered. For example, in DBX, right now, over 90% of the entries that are on by default are for third-party drivers. Now, data sources that I used for my research included, number one, VirusTotal. But eventually, I also got internal access to the assigned images. I want to give you an example. So back in 2022, there was this talk called One Bootloader to Rule Them All by Shim. They discussed two vulnerabilities they found in third-party code. In both cases, there were two UEFI shells that had unrestricted functionality that allowed you to gain code execution. They reported it to Microsoft. We issued a revocation. But we have a problem with our process. We do not hunt for variants when revoking images. And I was able to find variants of these revoked modules by simply taking unique strings and then putting them into VirusTotal and my internal access. Now, fortunately, in this case, most of these variants are not on VirusTotal and publicly accessible. But it really does highlight an important gap. There are a lot of images that we've revoked that have variants. The reason for this is because often, when you think about normal programs, let's say Microsoft Teams, there's going to be a way different number of variants for development, with different versions with the same vulnerable code. And when we only take reports at face value, here's a vulnerable image, without doing the variant hunting, what can happen is we might revoke the hashes that we're aware of, but we miss images that have the same vulnerable code, and we leave our customers exposed. Moving on to the Linux Shim. So the Shim is a software package that works as a first-stage Linux bootloader. Microsoft signs Shim builds from Linux distributions. And the Shim includes these distributions certificates, which allows them to manually load UEFI drivers signed without Microsoft's intervention. You can see a diagram on the right from Red Hat, which kind of shows the flow of how this works. So the Shim has, again, embedded vendor certificates, let's say Red Hat. You provide it a grub2 image, and it'll verify the grub image against its own set of certificates. It does not need to be signed with the UFCA. And if it has a valid certificate, it'll actually go ahead and manually map this driver in memory. Now, I also want to tell you about SBAT, which is a really cool mechanism they built into the Shim. So it's called Secure Boot Advanced Targeting. And the idea is that instead of being limited to just hashes and certificates in DBX, we want to be able to revoke by version. So SBAT revocations are stored in this SBAT variable. A benefit of this mechanism is that it uses significantly less space than DBX and is scalable. That problem I mentioned earlier about different variants and versions? Well, with this method, by specifying a latest version to revoke, what it allows you to do is just revoke every module that has a version built with a lower number. Now, the drawback with this method is that it doesn't have the same anti-rollback properties as DBX might, because it's an unauthenticated variable. If an attacker can get code execution at boot, even if measurements don't go through, the problem is they can go ahead and delete your SBAT variable. Now, let's say grub2 has a vulnerability. The idea is that instead of adding every single grub2 hash into DBX, which is unpredictable and unreliable, because you might not find every single one, you instead add just a single line to SBAT that specifies a new version and revoking everything before it. The Linux community also has a repository known as the Shim Review. Practically any distribution of Linux can ask for their Shim to be signed. Now, distributions fill out a questionnaire, like the UFCA signing process, and it requires approval from trusted developers. In 2020, there were major issues found in grub2 by Eclipsium. These were dubbed boot hole. Grub2 is loaded by the Shim, so to revoke the secondary grub images, you needed to revoke the original Shims. And what I found in my research was that not all pre-SBAT Shims were actually revoked in 2020. And Linux vendors have reused certificates from past Shim builds that have signed vulnerable grub code. Let's talk about that. So, for example, what I did was I went ahead and VirusTotal, I downloaded all the files that were signed with the UFCA, I excluded the images that were revoked, and I filtered for the string UFI-Shim. Next, I went ahead and actually checked the version and whether it had SBAT. And the reason this is possible is because the Linux Shim actually has not only the version, but even commit hash built into the binary in the data ident section. This allows us to easily take a bunch of Shim binaries and tell, how old is this? Does this have any known vulnerabilities? And once I filtered out the version and SBAT support, I unfortunately found that there were a lot of leftover images that were exploitable. Now moving on to the Shim review repository. This is an example submission following SBAT's introduction in 2020 in response to Boohole. The question is, did the vendor revoke old vulnerable grub2 images, or are they using a new key? The vendor said, we use the same key, but since old grub2s don't have SBAT, the Shim won't load them. Now, there's a big problem here. Why does revoking old grub2s or using a new key matter? Why is Linux asking this question in the first place? Now, it's mentioned in the question, actually. It says, in order to prevent grub2 from being able to chain load those older grubs. So what the problem is that Shim does not actually require that SBAT is present for what's called chain-loaded images. So if you take the Shim and then take an image that's signed with a vendor certificate but does not have this SBAT section with version information, it won't let you load it. But if you take the Shim, take grub2, and then chain load the no SBAT image from grub2, it'll actually let it go through. And this is an example where the Shim review process failed. They approved this submission even though an attacker could take this new Shim and new grub2 image and load old vulnerable grub images. Now, moving on to second stage images. Now, these are usually come after grub, and there's no Microsoft involvement in their signing. It's all the vendor certificates. And this is a bit of a double-edged sword. You know, we don't have direct visibility into these secondary images, and every Linux image is more attack surface for Windows customers, and vice versa. The solution is to do our best with VirusTotal. So what I did was I took our existing methodology and just added a step in between. So we download UFCA images, but this time we'll actually enumerate vendor certificates. How do we do this? Well, the vendor certificate section contains the DER encoded format of that Linux distribution certificate. Next, we feed that back into VirusTotal and then download the secondary images. We again filter for the UFI-Shim, we check version and SBAT support, and we look for images that either don't have SBAT or are running a really old commit. And again, there were quite a few of these images that unfortunately were left over and not revoked. This is another example of how you can find vulnerabilities in the Linux Shim by looking at secondary images or the images that are signed by the initial vendor certificate. So, as an example, until late 2023, Fedora used the same certificate created in 2012. Now, why is this a problem? Well, you don't need SBAT support when chain loading, and an attacker can use a pre-SBAT grub image with the latest Shim. And the reason I called out this example, even though I went through an example with the Shim review repo, is that that example was with a smaller distribution. And I want to show that these sorts of human errors can happen even with the largest distributions out there. So to recap, there are still vulnerable Shims built before SBAT support that never got revoked. Vendors reuse the same certificates as same self-signed certificates across Shim builds, even when there's a security fix. You know, look for commits with a security impact that weren't handled as a security issue. And sometimes revocations are only done with SBAT, and that leaves Windows users exposed. Now, despite what you may think from the internet, Microsoft has a very close relationship with several Linux distributions that develop the Shim. A really interesting problem for us with the Shim and even the UFCA images is balancing customer choice with customer security. To what extent should we put the vast majority of customers at risk to support minority use cases? It turns out this is a really hard problem to solve. For example, one interesting question is, why should all this code from Linux be exposed to every single Windows user out there? And that's not just Linux code, though. It applies vice versa, too. Why is it that every single Linux user is exposed to every single line of code we put in our boot manager? And it turns out there really isn't a good answer. So I also want to call out, we talked about UFCA images, and we talked about the Linux Shim. But while the third-party story is bad, we're far from perfect ourselves. We don't often revoke old, vulnerable Windows boot managers because of compatibility. These are ecosystem challenges, is my point. I don't mean to call out just one area and be hypocritical about our own. This is an industry problem, not a vendor problem. Let's talk about some of the architectural challenges that make our lives really tough. So when it comes to our response capability, a huge problem is that there's been a significant increase in vulnerabilities for secure boot. And it's not that there's more vulnerabilities, rather there's more people looking at existing code. There's already hundreds of revoked images and our space is running out. DBX was really only designed to revoke 600 to 800 unique hashes. So the reason that is because before Windows 10 1709 hardware requirements for OEMs, they were only required to really support up to 32 kilobytes of space per UFI variable. Now, DBX allows us to revoke by hash or certificate, but we again run into that problem where there's a lot of variants of the same image, whether that be a variant like a development build or even a different version. And so one vulnerability can end up impacting so many images, it really does tie defenders' hands behind their back. You can see on the right is a graph of the DBX size in the last few years. We're already almost halfway there. And if we decided to revoke a certificate, for example, that's going to take up even more space than a regular SHA-256 hash. Now, outside of limited space, there's also another problem. DBX doesn't work for everything. So a great example is option ROMs, and this is what allows your graphics card to be able to interact with your machine seamlessly. What happens if there's a vulnerability in an option ROM? If we revoke it, any hardware that uses that option ROM will suddenly not work anymore. And unfortunately, no one thought it would be a great idea to separate option ROMs with a separate CA until now. This again goes back to the problem of how do we balance customer experience with security. I want to talk about the UFI security response team. So something I found really interesting is that, in this paper, Decoding UFI Firmware, they recommend that the standard embargo for UFI vulnerabilities is 300 days, compared to the 90-day standard industry disclosure timeline. Why is that? Well, they talk about how there's so many parties involved, and it's true, by the way. This community is very decentralized, and that can increase our time to respond. But what they're really saying is, because the system is broken, 90 days doesn't work. I think this is the wrong way to look at it. I think we should ask ourselves, why is such a broken process acceptable? We need to look at how we can streamline our processes and not make excuses for failures in our process. The second big problem is just the attack surface. There's so much code that is signed with the UFCA. We also lack proper governance over secure boot. When it comes to revoking, just as an example, that variant problem is a really serious issue. And unfortunately, we're also often at the mercy of our partners. So, for example, a vast majority of our customers will never use Linux in their life. And a lot of Linux users will never use Windows in their life. But we're still exposing ourselves, or each other, to our attack surfaces. I really do ask, why is this okay? And the third big problem, complexity. So secure boot has only really been around for a little over a decade. Understanding how it works is challenging and has a steep learning curve. Impact is generally limited to privileged attackers. But many of the issues we've discussed aren't crazy vulnerabilities. they come from fundamental process gaps. I want to show you what these challenges can look like in practice with a case study of a critical Linux shim vulnerability I found. So when I was investigating the Linux shim for low-hanging fruit, I began with their threat model. What attack vectors were relevant to them? What I like doing is building a mental map about how the component works. So first up, the GNU EFI library is initialized. This is the basic runtime support for things like allocating memory and other important functions. Next, the Linux shim goes ahead and updates SBAT and checks if the image itself has been revoked. Next, it'll initialize the mock state. And what this really represents is the certificates that are allowed to run on your computer. So this includes the vendor certificates that are embedded inside of the shim, but it also includes something called a machine owner key. So this is a functionality with the Linux shim where you can add your own key, and as the machine owner, and with physical presence, you have to accept the prompt at next boot, and you can now load images signed with your own individual key that you generated. Next up, we parse load options, and we installed the shim protocol. The shim protocol is interesting. It's what allows secondary images and grub2 to be able to verify an image using the same code that's already in the shim. And the shim protocol is also where there is an SBAT exception. If you verify something with the shim protocol, just because there's no SBAT doesn't mean much. Next, we'll verify the grub2 authenticode signature. It's really interesting. They actually re-implemented authenticode inside of the shim. This involves parsing the PE image and also parsing the certificates that are inside of that image. If the signature is good, then it'll go ahead and manual map it. If it's bad, it'll go back to a fallback module, which again is, of course, verified. Now, there were a couple of things that I really wanted to look at. Number one is secure boot advanced targeting. So SBAT is CSV format. So I was wondering, if I tried to load a malicious image and SBAT was parsed, is there an attack surface there for me to fuzz? Some of the areas I didn't look at include the library initialization, mock initializations, and the load options. I also looked at authenticode signatures, the PE parsing. I felt like that was ripe for attack. And finally, I also focused on flexible file systems. So one really interesting fact about the shim is that it can support a lot of different file systems. It all depends on what you use to start the shim. So if I go ahead and start shim with HTTP boot, then it'll actually try to load grub from HTTP, the HTTP server that it got the shim from. PXE and HTTP use a virtual file system, UDP and HTTP respectively. A quick tangent. How do you fuzz an EFI bootloader? Well, I found two really good tricks for doing this. Number one, you start with your unit tests. Generally, they're actually designed to run independently. Number two, you can also just copy out the component that you're interested in into your own project. This works great when you have just a limited set of code for your module. So in the case of SBAT, that's exactly what I did. I went ahead and created a project. I configured the AFL++ compiler, and then I copied over the SBAT code. Now for authenticode parsing, I used unit test, and I just made a small harness by taking a unit test, replacing the main entry, and then throwing it at AFL++. But unfortunately, with these fuzzing techniques, I really only found out-of-bounds reads, which isn't that impactful at secure boot stage. But let's talk about network boot. So Shim has a really small footprint, and what I decided to do is let me first manually review the code for networking support. So interestingly, UFI actually has support for HTTP. Your firmware has to implement it, but it's there. And since Shim uses the device it was started with, I was curious, what attack surfaces are going to be exposed to PXE, which is using UDP, and HTTP boot, which is using an HTTP server. So what I decided to do was look at the logic. And this is pretty simple, right? It initializes the HTTP protocol. It'll configure it. It'll send a request and then receive a response. But what I was curious about is when untrusted data starts to come into play, which is receiving a response. Let's take a look at that a little bit in more detail. So what the shim does is it'll store headers in a temporary stack buffer. It'll then allocate a buffer using the content length from the server, and then it'll copy the sent data from the server into this buffer. I have a question for you. Can you spot the vulnerability? So what really caught my eye was this middle part, allocating a buffer using the content length from an untrusted server. So the server has control over the buffer that the response is copied into. This is a really big problem. So what the code really does is it'll go ahead and enumerate your headers, it'll look for content length, and then parse that into an integer. Next, it'll parse that directly into an allocate pool call, which is just malloc. Next, it'll go ahead and copy over all of the received data into this buffer that was allocated with an untrusted size. These two facts do not make for a great story, and it leads to an out-of-bounds write. So, triggering a debug. How do we abuse control over the received buffer using the content length header? I wrote a small Python HTTP server to do this. Number one, we'll return a content length of 1. And we'll also return a content length of 9213. And the idea is that the first one, 9213, will actually be processed by the firmware, and that's how much data it's going to receive. And then the 1 is for the shim. When shim goes ahead in the headers, parses them out, and then allocates a buffer, it'll allocate a buffer of 1 byte. So what this code really does is, if boot x64 EFI is requested, then it'll go ahead and return the shim. If grub is requested, that's where the exploit comes into play. So we first send the content length, and then we'll send the content length of 1. Ideally, this leads to an allocation of 1 byte, but then a copy of over 1,000 bytes. I want to go through a quick demo with you. So what we have here in this setup is an attacker server where it's running the HTTP server with these images. I also have Wireshark running in the bottom, which is just monitoring the network for DHCP and HTTP requests. And the reason for that is because Pixie boot and HTTP boot, how do they know where to connect to? Well, it'll actually do a DHCP broadcast, and with specific options to get those properties. And on the right, I have a victim running EDK2's OVMF project, and it's just starting HTTP boot over IPv4. So things are going to happen really quickly, but we're going to break it down. So the exploit ran. Let's go through it. On the left, the attacker machine, what we see is that, number one, the machine requests boot x64.efi. This is the regular shim image that it retrieved that the DHCP server was configured to return. No exploit here. But next is the grub x64.efi, and this is where our exploit code comes into play. This is where we return a content length of 9213 initially for the firmware, but also a content length of 1 for the shim. We can see this reflected in the network traffic as well. What we see is, after the exploit started, was a DHCP request and a DHCP acknowledgement. The acknowledgement is where we return the URL of the HTTP server the client should connect to. You can also see the same requests that were outputted in the top left. Now on the victim machine, you can see that an IP address is assigned. Then it'll go ahead and make the GET request for that shim image. It'll download it. And then there's also a log message that I included for clarity, which is in the receive HTTP response function. And what it shows is that it's going to copy memory where the buffer was allocated with only 1 byte, but the number of downloaded bytes was actually 1,460. And this is where the out-of-bounds write occurs and the victim machine crashes. A patch was actually released in January 2024. if you go to the Shim today, you can not only view the vulnerable code, but you can view the commit that discusses the patch. Now, the big question is, are customers really protected? So, good news, the code that's vulnerable comes after the SBAT revocation checks. So we can use SBAT to revoke these images. But unfortunately, we'd need to revoke every Shim built in over a little less than a decade. And the reason that's a problem, well, besides the obvious, is if I have like a USB stick with Linux on it and I don't update it, if I try to plug that into an updated machine, it's not going to work. You know, again, we keep coming back to the customer experience versus security challenge. Now, for Windows, what we're planning to do is targeting SBAT support this summer and actually revoking these images. But we're going to do it in a little bit of a special way. We have a certain compatibility checks that's designed to reduce the risk of bricking a Linux user. You know, we're going to check for the presence of Linux. We're going to be really careful. But there's still that risk. Unfortunately, I don't have a clear timeline for the Linux story. But I do know that a lot of vendors are right now releasing new shims without this vulnerability in it. So I also want to go back to the whole idea that the Shim uses the device it was started with to load images. You know, it would be kind of lame if this issue only worked with HTTP boot. I mean, who the hell uses HTTP boot? This is where grub comes into play. So grub has a device syntax that allows you to specify a path on a remote server. And optionally, you can build grub with HTTP and TFTP. You can see the syntax below if I wanted to go ahead and download a file from grub.example.com. Now, what I found was that you can actually use HTTP boot from the local, adjacent, and remote vectors. How? It's a trick. So what we do is, let's say we're in the local vector. We start the Shim from the hard drive. We start grub from the hard drive. But then we have a grub configuration that specifies, hey, chain load using the HTTP device syntax. And the same thing works for Pixie boot. We again serve the image over the network. We serve a grub configuration over the network. But in the grub configuration, we tell it, run the Shim again, but this time from my HTTP server. And the reason this is really cool is because practically every attack vector that secure boot is exposed to, you can abuse this vulnerability with. So it's not just machines running with HTTP boot and having that configured. Effectively, if you're a local attacker, physical attacker, adjacent attacker, or remote attacker, let's say I'm in your ISP as a nation state, you can abuse this issue. So, to review, this code is not new. It was committed 8 years ago at least. It's another example of a trivial vulnerability with a significant impact. And like a lot of other secure boot issues, it's really challenging to fix. The rollback attack strikes again. So, you know, we have Linux vendors that are releasing new shims without this vulnerability. But the big problem we keep coming back to is that the rollback vector allows for an attacker to go ahead and just bring an old vulnerable image. I also want to say a very massive thank you to the Shim maintainers who patiently answered all of my questions. I don't think I would have found this bug without their help. And for that trivial vulnerability significant impact problem, I think there is also a lesson to learn for the broader industry. You know, I think that it's really interesting how you can have a very technically complex bug that has a completely different business impact. And it's, for example, take this vulnerability or a random local privilege escalation vulnerability and compare it to a cloud vulnerability. You know, cloud vulnerability can be as simple as you're missing an ID check, or you're not verifying that the organization a user is requesting through the API is actually, the user's actually in it. But it doesn't matter because the business impact really is disjointed from the technical complexity. So where do we go from here? I want to talk to you about how we shifted security left for secure boot. Before MSRC invested in secure boot, engineering had this interesting revocation mechanism called the secure version number, SVN. Now, it's an early self-revocation check that in first-party images that use a custom UFI variable, just like SBAT. There is no reliance on DBX. But here's the problem. It wasn't enforced across all images. There was a lot of attack surface that came before the SVN check. And like SBAT, it can be bypassed by design because the SVN variable is unauthenticated. For example, if I was a physical attacker, what I could do to bypass this is, number one, bring the Linux shim, install my own machine owner key, execute code, and then just delete the SBAT or SVN variable. Now, obviously, if you use a mock key, then if you use measure boot with that, it's not going to unseal your secrets. But if I delete the SBAT and SVN variables, I can just go ahead and use an old vulnerable image from either Windows or either Linux, and measure boot can only do so much against that. So here's where revocation by embedded secure version information comes into play. I call it revise. So this was a proposal from MSRC to combine SVN with DBX. Now you might say DBX is used to store hashes and certificates. How do you involve a version? Well, we can revoke any hash we want through DBX. SHA-256 hashes are just 32 bytes of random memory. The idea was, what if we went ahead and smuggled version data through this fake hash that only our code recognized? So how this works is that anyone else looking at DBX is just going to think this is another hash. But our code will recognize this is a special entry in DBX, and it will go ahead and parse out a structure from the hash data. And the reason this is really, really interesting is because it allows us to maintain compatibility. You know, when we've been discussing a lot of improvements for secure boot, we've run into the problem of, well, changing firmware, et cetera, is going to take a lot of time. You know, it'll largely only affect new devices, et cetera. But what this allows us to do is leverage the security properties of DBX, but this time, use it to store version information. So in our case, we're using a special GUID in the signature owner member to specify which entries contain version data. And then our signature data contains an opaque structure. It has information about what version we're trying to revoke. And surprisingly enough, it was actually released fairly quickly. It was released last month in April 2024. You can see a decompiled view of the code on the right. And the really cool part is that the Linux community actually likes this concept, and we're looking at opportunities to bring that to them. Can we combine SBAT with revise, like we did with SVN? And the reason is, again, is the anti-rollback properties of DBX. And what we've really learned from this is that there's a lot of value in taking your security experts, your subject matter experts, and then combining them early in the development process. Now, longer term, let's talk about a 2 to 4 year time frame. There's quite a few recommendations that MSRC has made in order to improve our secure boot security story. Number one, we want to leverage intentional fragmentation of DB and DBX. So what does this mean? Well, there's a gap for something like an adaptive secure boot, something that can adapt to your machine and make sure that you're not being exposed to attack surfaces more than you need to. This is not just the UFI CA, but also Microsoft CA is involved here. So what we're thinking is, can we have a system where we use signed update payloads in order to reduce the attack surface of your machine? You know, this could be removing something from DB with a DB set payload, or revoking something extra when you want to. You know, can we add a group policy that allows you to revoke the UFI CA? And can we also have a signed payload we can give to Linux so that they can revoke the Microsoft CA if they'd like? But next, we also want to be really transparent about all our changes. These are really hard problems, and we need to stop viewing them in isolation. We want to revisit minority use cases and customer impact. This isn't talking about Linux. Linux isn't going anywhere. They're a fundamental part of our ecosystem. But what we are concerned about is the random images we sign with the UFCA. Some of these images, like 2 people use it. Why are we exposing every single customer to these attack surfaces? I think we need to revisit these use cases and then really balance them against the customer impact. Is it worth it? Should we be deprecating these use cases? Next, I want to invest in secure and measured boot. This is going to take time, but measured boot really allows us to have an extra layer of defense on top of secure boot. And the final recommendation I'll cover in this talk, you can view the rest in the slides, is that I think we need to put our foot down a little bit more. We need to hold partners accountable, and we need to make sure that partners aren't putting customers at unnecessary risk. Now again, this isn't going to happen tomorrow, but I'm interested to see in a few years, looking back, how much of this we can get done. We really think that secure boot has a lot of systemic problems that we need to address as a holistic basis, rather than just point fixes. Now, one real big problem that we've been working on is the fact that there might be more third-party UFCA modules with vulnerable code than there is space in DBX. How do we address this? Medium to long term, we could think about revoking DUFCA. It's already being rolled in the next 2 years. But this breaks old option ROMs. MSRC has recommended that in the short term, we should invest in measured boot. And what does that mean? Well, if you are a Windows user or your organization uses Windows, fun fact, enabling BitLocker with just default settings will actually kill almost every UFCA vulnerability we discussed. Now, you're still vulnerable to other issues like firmware bugs or first-party images. And for that second part, we're also looking at, can we use BitLocker to help make the story around rollback attacks a little better? But the cool part is, the way BitLocker works is that it'll remember what actually went into your machine when it booted last. And then it'll prevent unsealing of secrets whenever there's a disruption to that. Let's say someone introduces UFCA code in the boot process. And the cool part here is that, let's say the Linux Shim vulnerability I found. I want to use that and then boot into Windows. Well, I can't actually do that if BitLocker is making sure that only the certificates that it remembers are being used when decrypting the drive. Unfortunately, for Linux users, it gets a little bit more complicated. They don't actually have an easy mechanism like BitLocker that you can just turn on. I've heard rumors that Canonical is working on a mechanism, and when that's released, that might be a great option. But I also think that this might be a gap Linux can improve on in the longer term. We need a solution like BitLocker that can protect customers, not from the third-party attack surface necessarily, but even from Microsoft's attack surface. We have vulnerabilities just like the Linux Shim. If they had a mechanism like BitLocker, we could prevent a lot of these attacks simply by enabling measured boot. Now, what should you do if you want to find similar vulnerabilities, besides the examples we discussed? Well, number one, a really, really easy way to find low-hanging fruit in the third-party code base is to review old signed binaries. There's hundreds of unrevoked modules with obvious vulnerabilities. And platforms like VirusTotal are a great place you can start. I would say try to find variants of binaries revoked in DBX. It's not part of our process, and chances are there's quite a few modules that we haven't revoked. Number two, look at second stage images in Linux signed with their vendor certificates for the same problem. If you want to find new vulnerabilities in new code, check out Grub2. I guarantee you we're going to keep seeing vulnerabilities. There's so much parsing code in it. There's so much code that an attacker could potentially abuse. I guarantee you we're going to continue to see vulnerabilities in Grub. I also think that an interesting area for research is chaining together signed modules to enter an unexpected state. For example, one interesting thing I found was if you chain load shims together, you can actually combine the vendor certificates within them and load code with either vendor. There's interesting properties that arise whenever you use signed modules in unexpected ways that I think might have more vulnerabilities to be discovered. Now, for first-party code, unfortunately, we don't have time in this talk, But I do want to talk about that too. That was part of our research. It's a little bit different story. And also keep in mind that if you have a specific target, you can also go after that specific target itself. Especially if you have an OEM in mind, anything that they are responsible for managing is a really good place to look. That includes firmware and custom certificates. And now, the elephant in the room is that we keep focusing on short-term fixes, but I think that Secure Boots needs an overhaul to remain defensible. A lot of the problems with our patching capability really come from the fact that we have our hands tied behind our backs. We have limited space in DBX. These mechanisms are outdated. You know, who thought it was a good idea that only having space for 600 to 800 hashes was a smart way to go? I think that in the future, we really need to invest in a better specification. And a lot of that is also going to come down to partners. You know, even if we designed the coolest technical solution, if our partners take long to implement them, we're going to be in trouble. And that's the last slide. I'll now open it up to questions, if you have any.
Hey, thanks for the great talk. So you said you had this bug with like content length, and you actually had to send this header twice. Does this mean that there was one parser that took the first header and then another parser that took the second one?
Yes, so how that worked was that there was a parser in EDK2 that took the first one, and then since Shim just kept enumerating headers and didn't stop when it saw the first one, you can see here in the comments as well. Yes, so EDK2 used the first one, then Shim respected the second one.
Okay, thank you.
Hi, great talk. Would it be possible to ever increase the size of DBX so that you could have more hashes?
Yes, so what I mentioned with DBX was that before Windows 10 1709 hardware requirements, you actually had only 32 kilobytes of space. But Microsoft realized a few years ago, maybe 5 years ago, 5 to 10, that we need more space. And we actually did invest in that. Our new hardware requirements say that you need a higher individual variable size. But the problem for us is that, you know, you're only as safe as your weakest link. So there's still, you know, thousands, if not millions, of devices that come before these hardware requirements that have that limited space in order to revoke those hashes.
Thank you.
Hey, you mentioned all these different versions or variants almost of revoked images. Is there a way for users to manually add entries to the DBX right now in case they want to try to be extra secure?
Yes, so if you have Secure Boot disabled, you can actually go ahead and edit it freely. And I'd also say that with DBX specifically, your BIOS might have an option to go ahead and modify it. Same thing for some of the other signature database variables.
Wouldn't it be better to revoke vendor certificates that issue that produce those signatures instead of invalidating individual hashes of binaries produced signed with these certificates?
So the vendor certificates, are you talking about Linux Shim vendor certificates, or?
For example, yeah.
So revoking with the Linux vendor certificates, are you asking why that's worse or better than just revoking by version?
Because if you revoke a certificate, just one certificate, you don't have to keep like hundreds or thousands of hashes.
Oh, I see what you're saying. Yeah, so the reason that they don't do that, or we don't do that, is because we think that version data is a better discriminator compared to just a vendor certificate. So for example, that Linux Shim issue I found, that impacts tons of vendors. So going through, and it wouldn't make sense to revoke each vendor certificate. And I don't think we've seen any case where it's just one specific vendor. And if there was one specific vendor, at least with SBAT, you'd actually be able to revoke for just that vendor and for a version of choice.
I see. Thank you.
Yeah.
So you mentioned about the kind of Windows users booting only Windows and Linux users only booting Linux. Is there kind of any work done on kind of tying down that if I only want to run Debian, I there would be an easy way to not run anything else except Debian.
Yeah, so that goes into the whole adaptive secure boot idea. You know, the reality is you don't actually need to expose yourself to a lot of this attack surface. You know, why do I need to be able to run Joe Schmo's disk cover utility? You know, it doesn't really make sense. And so you're absolutely right. There is a gap for that. And I think that that's where we want to continue exploring, is an option for not just Linux and not just Windows. It's everyone. How can we make your computer only respect a limited scope compared to the current state where all UFCA code impacts Windows users, and all Microsoft code impacts Linux users. So with your idea of it specifically for like a Debian-only thing or like another vendor, the biggest challenge there would be that you'd have to create signed payloads for every single Linux vendor. And I think that it's going to be an interesting avenue, but we first need to do the bigger story, which is the UFCA and Microsoft CA. If we can pull that off, I absolutely agree. Narrowing that scope down further is a great path to make our customers even more secure. Cool. Any other questions? All right. It does not look like we have any other questions. Thanks so much to everyone for coming out to this talk. I really appreciate your time, and have a great rest of your day.